Hey Algebra 2, here are your notes for lesson 7.6, fractional exponents, day 1. So a rational expression that contains a fractional exponent in the denominator must also be rationalized. So when you simplify an expression, we have to be sure that our answer meets all of the given conditions, and then obviously those are listed there. We're pretty used to those, I'm not going to go over them, but you can read through them now. So rational or fractional exponents follow all of the exponent rules that we've already been using for integer exponents. But the new concept that we have to work with is this one. A square root is equal to an exponent of 1/2. Okay, if that's not very intuitive, don't worry, we're going to see why that's true in a minute. But using that understanding, or what that gives us, what is the rational exponent equivalent to the cubed root of x? Well, if you don't know it, that's okay. Think about it for a minute before I tell you that it is x to the 1/3 power. Now, why is that true? Well, let's look at something. Let's look at this idea of x to the 1/2. If I take x to the 1/2 and I square it, that is the same thing as x to the 1/2 times x to the 1/2, which is equivalent to x to the 1/2 plus 1/2. Okay, well, x raised to the 1/2 plus 1/2 is just x. So essentially, x raised to the 1/2 power is a number whose square is equal to x. Therefore, or so, x to the 1/2 is equal to the square root of x. Now, I want to show you something if you hadn't seen it before. These numbers seem to come out of nowhere. They don't make a lot of sense. But I'm going to show you a little bit here, and then we'll go into an actual definition. But these numbers are actually coming from the square root. The 1 is coming from the power of the expression inside of the square root. The denominator is coming from what type of radical we have. So let's see that again with 1/3, see if it makes sense. This time I'm going to go backwards, however. I'm going to start on this end. So if I take the cubed root of x, or x to the 1, we should get x to the 1/3. Let's see if that's true. We need to think of a number that multiplies to x that goes into it 3 times. Well, x to the 1 is equal to x to the 1/3 plus 1/3 plus 1/3. I can break that down into a multiplication problem of x to the 1/3 times x to the 1/3 times x to the 1/3. And if I multiply those, I get x to the 1, which is what I was hoping for. That is what is inside of my radical. But I notice if I take the cubed root of x, I'm going to get out this x to the 1/3 as my answer because there's technically 3 of them inside of the radical. So this is the same thing as saying the cubed root of x to the 1 is equal to x raised to the 1/3 power. So I've now gone in both directions for this problem. I've proved it both ways. However, it doesn't just work for x squared and the cubed root, these two numbers. It works for all of our radical expressions, and we're going to see that now. So let's convert between rational and fractional exponents. Now, if you saw my trick here, that's the one I'm going to continue to use. I know that the number of the exponent, the exponent of the expression inside of the radical is my numerator. The index of the radical is my denominator. So for this one, I'm going to take out x, and I'm going to say that the numerator is 2, the denominator is 3. And it really is that easy. I'm not pulling your leg on this one. Same thing here. X, I take that expression, the numerator is the exponent, the denominator is the index. Now the last problem looks a little tricky because there is no numerator, But remember, even though there's no numerator, this is technically x to the first power. So when we use our trick, we can say x to the 1 over 5. And this aligns with our idea that we were talking about here. If we have the square root, it's x to the 1/2. If we have the cubed root, it's x to the 1/3. In this case, we have the 5th root of x, which equals x to the 1/5 power. Pretty cool. But we can go both ways as well. We don't just have to go to fractional exponents. We can take a fractional exponent that doesn't work for us in this form, and we can put it into a radical. So the denominator becomes the index, and the numerator becomes the exponent. Now, this doesn't look like it's very helpful right now, but I promise you when we start throwing numbers in here, this is going to be very useful to be able to convert between forms. Same thing here, if you haven't already done so, we get x raised to the 4th outside 5th root, and it doesn't matter which order you convert in, it's just how I do it. And this one would be x squared to the 3rd. Which makes sense because these two, this one's 3/2, this one's 2/3, these should be opposite. So we can check our work. All right, if you're still not quite following me, let's throw a definition into the work. So let's actually write this out and what this looks like without numbers, because sometimes the numbers can be confusing. So if I have something in this form, index, radical, expression, exponent here, I can rewrite this as x, it's a weird x, I'm sorry, raised to the m over n. However, I also want to give you one more piece. Because the radical and the exponent are kind of working together, I can also do the problem in a little different order, and we'll see this in a minute. I can take this piece first. So if there's a number in there, I can compute the nth root of x and then give it the exponent of m. So I can either do x to the m, then take the root, or I can take the root and then the exponent. And those are interchangeable. So let's now work with that a little bit. The nice thing about converting to fractions is that we can reduce powers and indexes, or indices, however you want to pronounce that. So we're going to practice now changing the rational expressions, exponents, and then reducing. So for example, this one, nxm 4x8. I turn that into x 8 over 4. However, 8 over 4 is quite obviously 2, so I can reduce this to x squared, which looks a lot nicer, sorry about that, nicer than this. Now, if we use what we knew from before, we can also prove that. We can say there needs to be 4 of something inside. I can break up x raised to the 8th power into x squared times x squared times x squared. When I take that 4th root, I can take out an x squared, so I know that's true. I love it when you can use new knowledge to prove old knowledge. I think that's kind of fun. This one, don't let it get you, even though there's no denominator. We know that a square root has this imaginary 2 outside. So when I rewrite this, it's the same thing as saying x raised to the 6 over 2, or simplified into the form x cubed. Same thing with this last one. We're going to simplify it to x to the 6 over 3, which simplifies back to x squared. I love it. So simple, so clean. Last one. Why did we do all this work? Why do I care about being able to convert between fractions in the exponent and these radicals? Here it is. If I had showed you something like these numbers a short time ago, you probably would have panicked and put it in your calculator. Here's the thing. We can now rewrite these and evaluate them in a much nicer and easier, more efficient manner. So, first things first, it's in an exponential form. I want to put it into that radical form. So I'm going to do that by putting 27 inside. That's the base, so the base goes inside the radical. The numerator becomes the exponent. The denominator becomes the index. Perfect. Now there's two ways to do this. We can either take 27 squared and then take the cubed root of whatever that is. But I want to bring your attention back up to this. Remember how I said you can take the radical operation and then take the exponent. And that's what I'm going to do here. I'm actually going to start by taking the cubed root of 27, which I know is a nice number. And once I find it, then I'm going to square it, because that's a much smaller number to square than 27. Just a trick that I find helps. So I know that the cubed root of 27 is 3. 3 squared, because I'm bringing that exponent down, is 9. Wow. Who would have knew that 27 raised to the 2/3 power could be just a simple number? You would think you're going to get some big nasty decimal with that, but we actually get really lucky. And fun fact, the same thing happens with these next two. So if you've been following along and you're feeling pretty confident, go ahead and pause the video here, try those two on your own. If not, hang with me, we're going to do them together in a minute anyway. So let's get to it. 32 raised to the 3/5 power is the same thing as taking the 5th root of 32 to the 3rd power. Again, I have no desire to take a number as large as 32 to the 3rd power, so I'm going to go ahead and take the 5th root of 32 first, and then take the 3rd power. Because I know that the 5th root of 32 is the beautiful number 2. 2 raised to the 3rd power, heck of a lot easier. In fact, 2 to the 3rd power is just 8. And that's my answer. There's an answer, there's an answer. And last, but definitely not least, 16 raised to the negative 3/4 power. I don't want you to freak out over the negative, because guess what? We can deal with that negative at any point in the problem. We don't have to deal with it first or last. We don't have to follow any rules like that. So let's just start off the way that we know how. The 4th root of 16, and I'm going to go ahead and put the negative 3 in here. But again, how I said, we don't have to deal with it in any particular order. I would much rather take the 4th root of 16 and then take all of it to the negative 3rd power. Because when I do that, 16, 4th there, is 2. 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. Raise it to the 2 to the negative 3 power. If you remember from our exponent unit, anything to the negative exponent just takes it and flips it to the bottom. So this is the same thing as saying 1 over 2 raised to the 3rd power. 2 raised to the 3rd power, we already saw in the last one, was 8. So the only difference in these two problems is instead of having 8 over 1, I have 1 over 8 as my answer. And there you be. I absolutely love working with fractional exponents. However, I understand that they can be a little bit confusing, especially when you're going between those forms that we talked about. So if you have any questions, please don't hesitate to let me know.